Welcome to video 5.1. Our discussion here will focus on measuring energy changes. Some of this might be review if you were around for Chem 2. Hopefully that'll help you a little bit. But just remember, I studied endothermic reactions before they were cool. In terms of accessing prior knowledge, your memory of the mole will be helpful. Kelvin and Celsius as temperature scales will be helpful. A couple little things here that we'll discuss as we go through this section. The big idea: enthalpy changes from chemical reactions can be calculated from their effect on the temperature of their surroundings. Remember this equation? Q equals mc delta T. Yeah, that's what we're working on today. In terms of the first set of understandings, heat and temperature, we'll talk about, give you some background. Energy is, in sort of a physics definition, the ability to do work, such as to move an object against an opposing force. Many forms of energy, heat, although depending on who you ask, heat is maybe not energy. For us, we will consider it energy: light, sound, electricity, chemical energy. Energy released or absorbed during chemical reactions. Sometimes we call this chemical potential energy. Heat is a mode of energy transfer which occurs as a result of a temperature difference and produces an increase in disorder in how the particles behave. Disorder, we'll talk about that later in topic 5 and 15 when we talk about entropy. Heat increases the average kinetic energy of the molecules in a disordered fashion. They start moving faster. They're moving around, hitting the walls, hitting each other more often, more frequently because of the extra heat, because of the increase in kinetic energy. Temperature is a measure of the average kinetic energy of a substance because the movement of the particles is dependent upon temperature. So when using Kelvin, absolute temperature is directly proportional to the average kinetic energy of its particles. Increase the temperature, you increase the kinetic energy of the particles. Kind of restated here. Higher temperature equals higher average kinetic energy. Absolute zero is the lowest possible temperature attainable, as this is the temperature at which all movement has stopped. Do a Google search on how low can you go. How close have we gotten to 0 Kelvin? Not we like me, but scientists. It's pretty low. Now we're going to talk about energy in terms of chemical reactions. One of the things we need to handle with this is to define the system and the surroundings for reactions. So the system is the material or mixture of chemicals being studied. Sorry about the typo. So, if I'm talking about a reaction, we're speaking of the reactants and the products. If it's an aqueous reaction, the reactants and products are the system, but the water would be the part of the surroundings. Even though something is aqueous, the water itself is really not part of the system, it's the surroundings, and that's something really important. In an open system, energy and matter can be exchanged with the surroundings. An example of an open system would just be a beaker of water. It's open to the surroundings. Energy and matter can be exchanged. A closed system exchanges energy but not matter with the surroundings. Maybe this is a sealed jar. It's going to exchange energy because if you heat up the surroundings, the jar will heat up, but the matter itself will not be exchanged because it's stuck inside the jar. An isolated system is something we probably won't encounter in this class. It does not exchange matter or energy with the surroundings. We really don't have that in this class. So let's remember a term from Chem 2 if you were with us, or a new term if you weren't, called enthalpy, which is essentially the heat content of a system, or energy content of a system, stored in the chemical bonds and intermolecular forces as potential energy. So changes in enthalpy are shown by delta H. If I increase delta H, if I have a positive delta H, heat or energy is being added to the system. If I have a negative delta H, heat is being released from the system. we'll be familiar with those terms as we move forward as well. So the system, the surroundings, and the system here might include the water, it might not include the water. If I add heat energy to the system, delta H is positive. This is an endothermic process. If the system releases energy, it will feel hot usually, or maybe it will release light. This is called an exothermic process. The system has less energy after the reaction than before, so delta H is negative. So again, endothermic and endothermic reactions, these are enthalpy diagrams, and we'll spend a fair amount of time talking about these throughout the unit. Total energy is conserved. So the amount of energy gained or lost by the system is equal to the amount of energy given or absorbed by the surroundings. So if delta H is negative, this energy is gained by the surroundings. If I have a positive delta H and it is an endothermic reaction, this energy is released by the surroundings. You might say donated. The surroundings donate energy to the system in order for the reaction to happen. But this energy being conserved is quite an important notion, especially for later with calculations. In the context of reactions, we would say a chemical or substance that is lower in enthalpy is more thermodynamically stable. More stable in terms of its energy. It has a lower potential energy, a lower chemical potential energy. This is another notion that will build throughout the unit. Kind of an introduction in 5.1. We must define standard conditions when we're talking about enthalpy changes. So delta H values are given usually for standard states, and that requires us to use this little not symbol. Delta H naught, given in your literature like your data booklets, measured under the following conditions: 100 kilopascals, concentration of 1 mole per decimeter cubed if concentration is applicable, and substances in their standard state. So oxygen, what is its standard state under these conditions? Well, under this pressure, it would be a gas. Temperature is not part of the definition, but 298 Kelvin is usually the specified temperature. What is water at this temperature? Well, usually liquid. That's what standard state means. So let's look at a couple reactions. Carbon dioxide plus water makes glucose plus oxygen. Where have you seen that reaction before? That is photosynthesis. Photosynthesis requires energy from the sun, so it has quite a high value for delta H, and it is positive. That means it is endothermic. That kind of makes sense. Photosynthesis requires energy from the sun, therefore it's an endothermic reaction. CH4 plus O2 makes CO2 plus H2O, negative 890 kilojoules per mole. That is exothermic. That is combustion. This is a combustion reaction. So, kind of makes sense that I have a negative delta H. So let's look at enthalpies of combustion and formation. Consider reactions in aqueous solution and combustion reactions. Well, here we go. Enthalpy of combustion is the enthalpy change for the complete combustion of 1 mole of a substance in its standard state in excess oxygen under standard conditions. So methane would react with 13 halves of O2 to make 4 CO2s and 5 H2Os. 1 mole of the substance being discussed here. So we can use our data booklet. Let's see, methane is here. We looked at, here's butane. Lots of possibilities. This is table 13, enthalpies of combustion for a number of substances. What do you notice about the values for delta H? The little C here, that means combustion. Every single one of these values is negative. Well, it makes sense. Combustion is exothermic. Enthalpies of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. This topic, enthalpies of formation, will become more apparent in 5.3 when we discuss Hess's law. But let's look at a couple examples. Water as a liquid is going to make 1 mole of hydrogen gas and half a mole of oxygen gas to make H2O. Negative 285.8 kilojoules per mole. Well, I'm burning the hydrogen to make the water, so that kind of makes sense that it's negative. But what if oxygen reacts with hydrogen and it makes water as a gas, as water vapor? Well, that's only negative 241.8 kilojoules per mole. Why the difference? Same reaction, except for this. In the first reaction, water was a liquid. The second reaction, water is a gas. Let's talk about this when we discuss our video questions in class. And if I forget to talk about this, feel free to remind me, because I want to discuss this difference a little bit more, with a little bit more depth. Our data booklet gives us enthalpies of formation in table 12. Who knew? Look what we got here. We have water and we have steam. Water as a liquid, water as a gas, different values. A number of different substances, but the state is given here. We also have delta G and we have S. We'll come to these later. Now, in terms of syllabus statements, we're going to learn how to use Q equals MC delta T, or maybe we'll review Q equals MC delta T. Heat changes can be calculated from temperature changes, as long as I have some understanding or some knowledge about the substance being studied. So when a substance is heated, the change in temperature depends on the mass of the object. Kind of makes sense. Heavier object, it's going to take more energy to change the temperature. It also depends on the amount of heat added. Burn something for 5 minutes, or heat something for 5 minutes, heat something for 10 minutes. 10 minutes is going to give you more heat. Or heat something on high heat versus low heat. Well, the high heat is going to give more heat, create a bigger temperature change. But it also depends on the nature of the substance. And this idea is called specific heat capacity, because some substances heat up faster than others, even under the same conditions, where the mass of the object is the same and where the temperature, where the amount of heat added is the same. So specific heat capacity is something we'll need to understand. Now we will use a calorimeter. Ours may not be quite as fancy as this, but we will use a calorimeter to study energy changes in reactions. And typically we have water with a thermometer, or even better than a thermometer, a temperature probe. It helps if we have some sort of shield to kind of keep, especially if I'm burning something, to keep the flame intact. Although some reactions might just happen in a styrofoam cup. Maybe it's insulated and it's an aqueous reaction. I can just measure it with a temperature probe. Now let's talk about specific heat capacity again. It is quite an important idea. And it basically is the property of a substance which portrays the heat needed to increase the temperature of a unit of mass, usually 1 gram, by 1 degree Kelvin, which, remember, is equivalent to 1 degree Celsius as an interval. Water has a specific heat capacity of 4.18 joules per gram degree Kelvin. So it takes 4.18 joules to raise the temperature of 1 gram of water by 1 degree Celsius, or 1 degree Kelvin. 1 Kelvin. We don't usually say degrees Kelvin, we just say Kelvin. So 1 Kelvin. Change color on you there. This is a pretty high specific heat capacity. Most metals are decimals, fractions of 1. Water is 4.18. It's quite a high specific heat capacity. Your data booklet gives you the specific heat capacity of water with two different units, joules per gram degree Kelvin or kilojoules per kilogram degree Kelvin. 4.18 in either case. So when we calculate heat change, we will usually use water in a calorimeter, but there are other scenarios that might involve that we might use for calculating heat changes. The formula we're going to use is Q equals mc delta T, where m is the mass of the object whose temperature is changing. Typically it's going to be water in a calorimeter. C is the specific heat capacity of the substance. Again, typically water. We could have a block of copper, and we could calculate Q equals mc delta T for a block of copper if we could study its temperature changes. In that case, the mass would be the mass of the copper, and the specific heat capacity would be the heat capacity of the copper. So this formula can be used in a couple different scenarios. Typically for us, it's going to be used for calculating in a calorimeter where the mass of the water and the specific heat capacity of the water matter. Delta T is the change in temperature, which is the final temperature minus the initial temperature. And this formula is given in your data booklet. Ta-da! Now let's talk about an assumption. It's quite an important assumption. Way early on we talked about the fact that heat lost by a system is equal to the heat gained by the surroundings. So the calorimeter is basically going to be the surroundings. So that means delta H equals negative Q. If I calculate Q equals mc delta T, and actually I really need to be clear here. Delta H is negative Q divided by moles. Sorry about that. You really need to include that divided by moles because delta H is per mole. So I apologize that I didn't have the slide correct there. That's something really important. But the negative sign here is really what I'm trying to focus on here, because if the system releases heat, the calorimeter will absorb heat and the calorimeter will raise in temperature, the water of the calorimeter specifically. So if the water raises in temperature, that'll give me a positive Q because delta T would be positive. But delta H would be negative if it's an exothermic reaction. So that means delta H equals negative Q divided by moles. Really important concept. Now let's try a practice problem. Thanks for hanging in there. A little bit of a long video. We're getting near the end. Let's do a little bit of a practice problem. Take a look at what's written here. Pause the video if you'd like to work ahead of me a little bit, and I'll come back and I'll give you some explanation. All right, let's see what we can accomplish here. Let's look at Q equals mc delta T. Mass of the water in the calorimeter is 200, that is M. Temperature increase was 13, that is delta T. So if Q equals mc delta T, it's 200.00 grams times C, which is 4.18 joules per gram degree Celsius, times 13.00. So my answer can have three significant figures. And my calculator tells me that Q is 10,868 joules. Let's think about units. Grams cancel, degrees Celsius cancel. Oops, that's degrees Celsius, it cancels. We're left with joules. So we have Q equals 10,868 joules. And I want delta H. Calculate the enthalpy of combustion. This is delta H of combustion. So this is negative Q divided by moles. Well, we just got Q, so negative 10,868 joules. We said we could keep three significant figures. Let's remember that, three significant figures, although I'm keeping the number here rounded with extra significant figures. Now, I need to divide by moles. So let's do a little bit of math here. 0.45 grams of ethanol. And I know that the molar mass of ethanol is 46.08 grams in 1 mole, and so 0.45 divided by that value is only 0.009766 moles of ethanol. 0.009766 moles. So now I'm going to divide and I get 1,112,883 joules. If I divide by 1,000 because I want kilojoules, I get 1,100 and let's call it 10 kilojoules. How many significant figures can we have? Oh, we can only have 2. Sorry. Let's call it 1,100 kilojoules per mole. 1,100 kilojoules per mole. So now it says compare your value with the IB data booklet and suggest reasons for any differences. So let's see, this was ethanol. Let's find ethanol. Ethanol says 1,367. We got 1,100. So our value is too small. Why? Why would it be too small? Well, the biggest reason is probably energy from the flame of the ethanol lost to the surroundings. Heat energy lost to the surroundings is a big problem for calorimetry, especially depending on your setup. So there you go. We've handled a practice problem. And that essentially wraps up the discussion. We've got a few little things at the end here like TOK. What criteria do we use in judging discrepancies between experimental and theoretical values? We just did that a little bit with the discussion at the end there, comparing our value to the theoretical value in the data booklet. International mindedness. Except for the US, everybody is metric. Don't even get me started. Connections to other topics. The mole, of course, physical states and changes of state, reactions. A lot of connections we can make. So as a summary, reactions are classified as either exothermic or endothermic. And the enthalpy change for a reaction, which is delta H, can be calculated through calorimetry and utilizing Q equals mc delta T, because delta H is negative Q divided by moles. That's a key formula. Any other details you want to add to the summary, feel free, put them in there. It's your notes. Make them as good as you want. Here's a checkpoint question for you. A pure aluminum block with a mass of 10 grams is heated so that its temperature increases from 20 to 50. The specific heat capacity of aluminum is 8.99 times 10 to the negative first joules per gram Kelvin. Which expression gives the heat energy change in kilojoules? Take a look, figure it out. Q equals mc delta T. This is a scenario where we're not looking at the calorimeter in terms of water, but we're just looking at a 10-gram piece of aluminum, and we know the specific heat capacity, so we know C. The correct answer? D. Q equals mc delta T. M was 10, so there's our 10. Times C, which was 8.99 times 10 to the negative first. There's our C. Times 30. Our delta T is 30 degrees. But I need kilojoules instead of joules, so I need to divide by 1,000. So that's why this question gives D as the best answer. Thank you for listening. That wraps up this video. You should have a Google form to fill out. I'd love to get your feedback. I would also really ask, begging and pleading, give me your answer to the checkpoint question. I want to know how you did. Thanks again. I'll see you in class.